All right, let's go ahead and get started. So if you guys are here in person, welcome. If you guys are joining on Zoom, glad to have you all here. So we'll start out with a quick administrative update or two, and then we'll get into today's lecture. So if you weren't here for the last lecture, we recorded that lecture, and unfortunately the lecture recording didn't, or the audio for the lecture recording didn't work properly. And so I went ahead and re-recorded that video just like an hour ago. So if you see me wearing the same outfit in that video, that's why. But the hope is to get that up and to you guys in the next couple of hours. So the awesome folks over at IT have figured out how to get everything live streamed, and it should be accessible to both Harvard and non-Harvard accounts. So if you aren't at Harvard, we should still be able to get that recording to you very, very quickly. And the same should be true of today's lecture. Cool. Okay. I think that's the only thing administratively. I do want to say before we start today's lecture, today is probably going to be the most dense lecture. It might also be the most difficult to follow. So if you're here for the first time, or if you have trouble following today's lecture, that is totally okay. Things will get both easier and more interesting, which I feel like is cool, because usually if something is more interesting, it's usually harder. But things will get both easier and more interesting after today's lecture. So just as a quick reminder, the next 3 lectures after today will be following that format of like puzzle, where we describe some sort of interesting phenomena in nature, we visualize it, and then the assignment will sort of be to create a piece of generative art out of it. But for today, we're talking about foundational concepts. So last lecture, we introduced the idea behind processing. We talked a little bit about how processing works. And today, we're going to be talking about how we can use processing to create some basic physics simulations. And then we'll also be visualizing our very first pattern in nature. If we have time, we'll try and talk about 3D stuff, but I don't expect that to be on the agenda. Maybe we'll push that to a later lecture. Okay, cool. So let's go ahead and start out on the blackboard first. The main concepts that we talked about last class were just the idea of being able to use randomness and how to animate in processing using the draw function. Now, before we dive into any of the coding that we'll be doing today, no slides at all today, it's just going to be Blackboard and live coding. I want to, here, let me go ahead and move this up. I want to go ahead and talk to you guys a little bit about why it is that we want to study the basics of physics. I was actually thinking of cutting this lecture out entirely. The sole reason being that I'm really, really bad at physics. I'm so bad at physics that I think in high school when I had to take my IB physics exam, I almost failed out of the IB program because of it. But physics is going to be an important part of the patterns that we talk about, and an important part of just what you might be interested in doing with processing in general. And so we'll take a look at how everything works in processing through the lens of just a bouncy ball today. And so what we hopefully want to do is we want to start out with the concept of just taking a ball. Hopefully you guys can see that. Let me move this up a little bit. Can everybody in person see that okay? Or is it better if I move to that board? Is this fine? That one?
I can.
Okay, cool. All right, awesome. So all we're going to do is take this idea of a ball, a circle, which we were able to create very easily in the last lecture. And what we want to do is we want to start by just moving it around the screen. We want to apply forces to it. So we're going to be doing this relatively imperfectly today. Some of the math can get just marginally more complicated than I think we have time to talk about in lecture, but it's super accessible if you just go online and look at some of the stuff. The only thing we're not covering today is trig. We're only going to be covering basic vector stuff. But the idea for today is we're going to take a ball, we're going to apply some forces to it, and then we're going to be talking about collision. If this ball collides with a boundary, how can we change the velocity of that ball and make it seem somewhat realistic? Then we'll talk a little bit about collisions with non-boundary objects, because this is something that comes up with a lot of the simulations that we might be interested in doing. And so we'll talk a little bit about how we might check for collision, do a little bit of collision detection between different objects. And this is going to be all portrayed through the lens of this bouncy ball, but it's going to be really, really useful outside of just this toy example, because a lot of the time when we're working with like any sort of interesting simulation that has hard body or soft body objects, we're going to be wanting to do some sort of collision detection. And so that's sort of the general idea that I want to start with. All right, I think that's pretty much everything that we'll be doing on the board for the first half. We're going to be starting out with this bouncy ball idea, and then we're going to shift completely to a pretty interesting pattern in nature. I'm not sure if you guys got a chance to read all of the pre-lecture readings and videos, but there was a reading in there about light rays and how they bounce off of coffee cups. It is my favorite pattern of all time. I talk about it a little bit in the TED Talk. It is a really beautiful visualization, and that's what we'll kick off the nature visualization part of this class with at the end of today's lecture. Okay, so let's go ahead and get started. I'm going to go ahead and share my screen. Hopefully you guys can see it. Let me share the entire desktop. Can you guys see that okay on Zoom? All right, perfect. Okay, also quick reminder, we do have this open source GitHub repository for this class. The idea is that after every lecture, I will have the code that we talked about and the slides for the lecture, if there are any, up on the GitHub, as well as assignments. Reminder, these are totally optional. They're highly encouraged if you have the time for it. I think they're a lot of fun, but also I wrote them, so obviously I think they're a lot of fun. If you guys are interested in doing them, please feel free. We have the debugging and work share channels in the Slack if you guys would like to share anything that you end up coming up with. Okay, so let's go ahead and create this bouncy ball simulation. So we're back in our processing window, and the idea here is for us to start as simple as possible. So we'll go ahead and, just like last time, we'll create our two main functions, setup and draw. And I'm going to be trying to explain as much of the code as possible, but again, if you're new to Java or you're new to coding in general, there's some of this stuff that you might just end up having to Google on your own time. The idea really is just, if you understand the concept and the reason that we are approaching things the way that we are, then everything should come relatively naturally. So as a quick reminder, this setup function is just going to run once. It's going to run at the very beginning when we press our run button. And then the draw function is just going to keep looping over and over and over. And so what we want to do for our ball, we can obviously represent our ball super easily if we go ahead and create a full screen canvas, and then we draw our ball as a circle in the middle of the screen. This is the first line of code that we wrote last class, I think. We can go ahead and represent what might be a ball super easily there in the center of the screen. Not super interesting at the moment. And so we're going to go ahead and instead of just creating a circle, we're going to go ahead and create a ball object. Remember, we created that walker object in the last class. And the way that we create a new class or a new object is just go ahead and create a new tab. And we'll go ahead and make this a ball. So let's go ahead and do that. So the big questions that we want to ask ourselves, right, are always, what objects do we need? What attributes do they have? And what functions do they need to perform? And in this particular instance, the object that we need is just a ball. The properties that it needs to have are obviously a position. We need to be able to know where our ball is on the screen. And we might also want some sort of force being applied to our ball. We might have a lot of different forces being applied, but let's start out with just one. So if you'll remember, in the last class we did this using two integer or float values. We just created a float x and a float y. And this is totally fine, but we're going to sort of graduate from that idea today and instead use vectors. And there's tons and tons of really good reasons to use vectors as opposed to just floats. The first one is that they're just going to be a lot cleaner. But second, and more importantly, processing is really cool because it has a bunch of vector operations. Like I said, I'm pretty bad at physics. If you are not, if vectors are your thing and you know exactly what to do with them to create some sort of physics simulation, every single function that you need, processing has. We won't be using a ton today, but I do want to get you guys acquainted with the idea. So a p-vector is what they call it in processing. I think it's a processing vector. But we'll need a p-vector to store our position. Now, vectors can have either 2 or 3 components in processing. We're just going to be working in 2D space, so our p-vector position will only consist of 2 aspects, an x and a y variable. And the other thing that we might want to do is create a velocity vector, some sort of velocity vector that applies a force upon our ball. And I think those are the only 2 attributes that we'll work with so far. Okay, so we know what the object that we want to deal with is. It's a ball. We know what the attributes are. 2 vectors, one that stores the position, the second that stores the velocity. And now the last question is, what functions do we want our ball to have? Well, like we said, 2 main functions. The first is the ability to move, and the second is the ability to display itself. Let's start with the latter, because that one's super simple, right? If we want to be able to display our ball, we can create a function that allows it to display itself. We can just call it display. And all we want to do is draw maybe a circle at the current position that the ball is at. And so the way this works with p-vectors is they have an x and a y component. They could also have a z component, but we won't be using that today. And so we want to get the x component, and remember that's the first parameter. The y component is the second parameter, and then the final parameter is going to be the radius. And just for the sake of organization, it might be nice to go ahead and define this radius in a variable, just so that we can change it later on if we feel like it. And so we'll create a float radius. And so displaying this circle is as simple as displaying it as a circle with a given center and a given radius. Okay, we also want to talk about movement. Before that, we need to go ahead and create a constructor for this object. Again, this is going to be, for some of you, Java minutia that you really don't need to worry about very much unless you get into the coding for this, and then you can tinker with that at that point. But the constructor is just going to give us a way to say, hey, computer, this is the object that we want to create. These are the initial attributes that it has. And so the initial attributes that our ball needs is an initial x and y position. And so we'll go ahead and say float init x and float init y. Remember, float is just going to be a floating point variable. Those are the 2 things that we want to take in for our ball. And so all we want to do is say that our position is a vector that starts out with this initial x and y value. And so we can just go ahead and initialize a new p-vector object with that initial x and initial y. If I'm going too fast for anyone, feel free to just let me know. I can go a little bit slower. I'm just trying to be super cognizant of time. Okay, so we have this new position. We can display our ball. Now let's go ahead and actually create a ball object. So here we've defined what a ball is. Now let's go ahead and create one. We'll just create a ball B. And we'll say that maybe this ball is a new ball that starts out, again, at the center of our screen. And all we want to do in our draw function is go ahead and display this ball. If we go ahead and run this, that didn't work. Why did that not work? Oh, okay. So yeah, that didn't work because our radius value here defaults to 0. We haven't set it inside of our constructor, so we need to give it an initial value. So maybe we say that our radius is of size 50. Let's go ahead and rerun that. Okay, cool. We have, once again, a circle in the middle of the screen. So you might be asking yourself, why did we go through all of that trouble for something that we could have done in one line? Well, here's where things get interesting. Now that we've created this ball object, we can ask it to move in specific ways, right? And so the ways we want things to move, and maybe we can turn your attention back to the blackboard here. The way that we want a particular object to move once we've applied some sort of force to it is we want to take some sort of vector for force. Maybe we're talking just about gravity here, and so we want a vector pointing downwards, and we want to take our position, and we say that we want to add our position vector to the force vector, which I guess in this case, because it's gravity, is just moving downwards. Yes, question?
Oh, no, sorry.
Okay, no, you're good. So all we want to do, right, is take our position vector and add to it our velocity vector. Now we haven't created that velocity vector yet, but let's go ahead and do that real quick. Maybe we can say that our velocity is literally just a new vector that has 0 effect in the x, but brings you down, has magnitude like 2 in the y. And so now if we add our velocity to our position at every single time step, we'll be sort of simulating gravity with this ball. Let's go ahead and see what happens if we do that. We'll do b.move and then display. Okay, this is pretty far from realistic, but our ball is moving, and it is moving downwards, right? We know that in the real world, we're not going to have this trail left by the ball. That would be pretty interesting. But we don't have that trail in the real world, so we want to get rid of it. Remember, the way that we can do that is we can, again, use that draw function to our advantage. We know that it gets called every single frame. And so what we want to do is we want to clear the frame, draw the ball, clear the frame, update the ball's position, draw it, clear, update, draw, so on and so forth. And to do that, we just have to clear the entire background. I'm going to set it to 0 every single time, which makes it entirely black. So if we go ahead and run that again, okay, that looks slightly more realistic. That's still not great, but it does give us sort of like the illusion of a ball falling. I don't think this ball is falling fast enough, so I'm going to increase the sort of like gravity, the faux gravity that I've created, and hopefully that'll fall a little bit faster. And I think what we'll do is we'll one by one tackle the things that are unrealistic about this animation until we finally get something that's somewhat realistic. The first unrealistic thing, right, is that this is sort of falling into the abyss. It's falling off screen and then it's completely gone. That's obviously not what happens with real world objects. When they hit the ground, they stay on the ground. And so let's go ahead and fix that. Doing that is going to be super, super simple. We're going to be taking our move function and we're going to be saying, hey, if we hit the ground, then we want to stay on the ground. We want to stop our position from changing once we hit the ground. So the way that we can do that is we want to say if our position's y variable, if our height is equal to, and this is where things might get confusing. We naturally might think of the ground as 0, right? That's 0 height. But if you remember from last lecture, the way that processing's canvas works is that 0, 0 is the top left, and width, comma, height is the bottom right, which means that things are actually flipped. The 0 is the very top of our canvas, and height is the very bottom. So when our position hits the height, then we want to say we've hit the ground, right? We've hit the ground, and so we don't want our y position to change anymore. And so maybe we can say how can we change this? We can say that our velocity's y component is now equal to 0. And that might work. Let's take a look. Okay, that did not work. And there's a couple of reasons why. So the first reason is, and this goes back to the processing minutia, is the way that we define a circle. This is the center point, and this is the radius. And so we're saying if the center point hits the height value, then we want our velocity of y to be equal to 0. But in reality, what we want is a couple of different things. We want our position at y to be greater than or equal to 0. If our center point is greater than or equal to 0, then we want to move past, or we want to stop our ball from moving. And the second thing is that it's not just our height that needs to hit, right? If we say that, again, directing your attention back to the blackboard, if we say that our center point is here, and this is the ground, we're not looking for when the center point hits the ground, right? We're looking for when the center point plus the radius of this circle hits the ground. So I think this is a more accurate calculation. And so if at this point you're sort of thinking, why are we going through all of this trouble to just depict the bouncy ball? Why can't you just have written this code to begin with? I think the important thing is not the bouncy ball that we're making. The important thing is sort of like debugging why this stuff works and doesn't work visually. It's going to be a very different paradigm, I think, to programming than you might be used to. And so that's the reason we're asking ourselves all of these maybe simple, maybe dumb questions. Okay, so we want to check when our radius hits our height. And so we can go ahead and modify our code pretty simply to do that. We could say when our position plus the radius is greater than or equal to the height, then we've hit the ground. Let's see what happens if we go ahead and run that. Okay, that looks like it works, right? Okay, still slightly realistic. Can anybody tell me something that looks wrong with this simulation still? Something that might be inaccurate about it? Yeah, exactly. There's no bouncing or acceleration. Usually when we have an object that hits the ground, it'll bounce at least a little bit, right? Especially if it is supposed to be a bouncy ball. So how do we want to deal with that? Well, anytime we hit the ground, if we want to bounce, that's the same as like multiplying our velocity in the y direction by -1, right? We want it to go the opposite direction now. And again, this is not the exact way that gravity works, obviously, but we're just trying to simulate it the best we can. So maybe we can say, listen, if we've hit the ground, then we don't just want to set our y velocity to 0. We actually want to invert it. We want to invert it. So let's see what happens when we try and invert our y velocity. Okay, that looks a lot more realistic, except now we flew off the top of the screen, which is not great either. So let's go ahead and real quick create a bunch of these boundary conditions where if we hit the top or bottom, it'll just bounce off each side. And so we can say if our y position is less than or equal to our radius, then we want to do the exact same thing, right? And the reason it's our radius, and I think you can probably draw out the picture to convince yourself that this is the case, but if we go back to our blackboard, if this is the very top, then I think as long as our radius has hit the 0 marker, then we are good. At least I think that's the case. It's been a little while since I've written this code. Let's go ahead and check to see. Yep, okay, cool. Everybody following this idea of just like our super simple bounce? Okay, so we're bouncing right now and we're good. And in fact, we can make this slightly more realistic by like losing a little bit of energy in every single bounce. I'll make this pretty dramatic so that you guys can see it very clearly. So we'll lose like 60% of our energy every single time we hit either the bottom or the top. Okay, that wasn't super interesting. We lost way too much energy there. Maybe let's only lose like 30% energy. Okay, that is not working. Let's see why. It could just be that even 30% is too much that we've lost. Okay, yeah, it really was just that 70% is too much that we've lost. And yeah, so as you can see, we're getting a little bit slower here on every single bounce. Okay. Still somewhat interesting, not that interesting. I think the real fun comes when we start changing our velocity vector. Instead of just simulating gravity, let's say that there's a little bit of wind happening, pushing our ball to the right. Now let's go ahead and see what happens to our simulation now. Okay, this looks good. This looks fine. That also looks good. We're flying off the edges on the right and left. We know how to fix this, right? This should be super duper simple. We can say if our x position plus our radius is greater than or equal to the width of our canvas, then we want to say that we've hit one side and flip our x velocity this time, not our y velocity. So we can say our velocity.x, and I'm going to change all of these back to 1s just so that we're staying as simple as possible as we can. And then we don't just want to worry about the right side, we also want to worry about the left side. And so we want to say if our position.x is less than or equal to our radius, then we've hit the other side, and we want to bounce off that. Okay, let's go ahead and check to see if this thing works. Yep, looks like we're mostly good. All right, so the fun part, right, of generative art that we talked about last time is its scale. It's really, really easy to take one ball and turn it into 100 balls and see what happens with simulations like that. So let's go ahead and do that. The two things that we're going to do now is 1, create that simulation. 2, learn how to move balls based on like where our mouse position is, add a little bit of interactivity to processing sketches. And then the very last thing that we'll talk about is how collision between balls works, because that's a lot more difficult than just having them bounce off balls. Once we do that, we'll be done with this sort of part of lecture. Okay, so maybe let's start with, before we add a bunch of balls, let's have this ball move with our mouse. I think that might be fun. So the way that we mess with interactivity and processing, and I absolutely love this about processing, is that it's as simple as writing a function. And so there's a couple of different ones that we can play with. One is mouse pressed, the other is key pressed. You can check which specific key is pressed, do all sorts of things. But for now, we'll just do mouse pressed. So every time, or while our mouse is pressed, this function will be run. And so maybe what we want to do is have our ball be attracted to wherever our mouse is. And so the first thing that we need is like our current mouse position. And processing is, again, really, really good about this. This is stored in 2 variables in processing, mouse x and mouse y, which just give the x and y coordinates, respectively, of the mouse position. And so maybe we can turn these into a vector, since we've been using vectors a lot. And we can call this mouse position. And that'll be a new processing vector, PVector, with the mouse x and mouse y positions, respectively. Okay, so the big question is, we have our mouse's position, we have our ball's position. How do we figure out how to get our ball towards our mouse? And this is where a little bit of vector math will come in handy. I think it might be as easy as taking the difference between our mouse position and our ball position, turning that into a vector and having that be our velocity vector. We just want a force pushing our ball in a certain area. We saw how we can do that using this velocity vector, right? The 5 pushed us down, the 2 pushed us right. And so now we just want a vector that pushes us towards our mouse. And so I think all we need to do is say that our new velocity vector for our ball, so our ball's velocity vector, b's velocity, is going to be equal to our mouse position sub and that sub is just going to be how we subtract vectors in processing. Mouse position sub the ball's position. And I think that might be it. So let's go ahead and go ahead and like run this. So our ball hopefully should move towards my, oh my god. Okay. So yeah, our ball does move towards my mouse here, except it's crazy now. It's going absolutely crazy. Does anybody have an idea for why that might be the case? This one's a little tricky, but why did messing with vectors like this make my ball go crazy?
Direction?
Not direction. That's close. We're going in the right direction now. Yes, exactly. Magnitude. Yeah. So our magnitude for our vector has gotten all crazy here. And so what we want to do is we want to set this magnitude to be somewhat consistent. And so maybe we can just do that by saying b.vel. That's just going to give us the velocity. And then we can set the magnitude in processing using this setMag function. And maybe we make it just something easy like 4. And so if we click over here, we are indeed moving towards our mouse. Okay, I think this is pretty cool. I really like this. I think we might be ready to add some more balls into the mix. All right, let's see. If we want to add more balls, then all we need to do is create, exactly like we did last time with our walker object, just a list of balls, right? And so let's go ahead and do that. And the way that we do that is by creating an array list. We'll call this balls and setting this to be a new array list. Okay, how many balls do we want? Maybe let's create an integer variable to store. We'll say numBalls equals maybe 10 to start out with. Super simple. And we can say for int I equals 0, I is less than numBalls, right? We want to just repeat this for loop for every single ball that we have. We want to go ahead and add a new ball to our list of balls. So we want to say balls.add, and then we want to create a new ball. And we want that ball, maybe this ball can just start in a random position. Again, we talked about how to do that last lecture. So we start with a random width and a random height. And it doesn't like this because I'm missing a parentheses. Okay, cool. So now we've created a list of balls. And now we want to say we can't just move B. B doesn't exist anymore. We want to move all of our balls. So we can say for every single ball B in balls, we can go ahead and move that ball and then display it. Now, mouse pressed is going to get mad down here because there is no B anymore. We just have balls. And so if we want to control, maybe let's only control one ball out of our group. We can say maybe we always want to just control the ball at the 0th index, the first ball in our list. So to do this, we can say balls.getZero. That's going to get our 0th ball. And then we want to manipulate its velocity and stuff. Any questions so far? Everybody following okay? Awesome. Okay, let's go ahead and run this thing. No, B, right, okay. So I used B again here. That needs to be balls.getZero. Okay, cool. Now this looks kind of cool. I like this a lot. But one last thing that we want to fix before we close up this part of the lecture is these balls aren't colliding. And this is where things are going to get just a little bit more complicated. Not very. We're just going to have to use distance formula a little bit and write another for loop. But this is the last bit of this simulation. Actually, let's go ahead and test to make sure that balls are moving to where we want them to move. Okay, so it looks like this one. I don't know if you guys can see my cursor, but this one right here is our control ball. This is the 0th ball. And so if I click this, you should automatically see, yeah, that one just started shooting over to the other side. And so I think this will be interesting because if we have one ball that we can sort of control and we have collision detection occurring between each of these balls, we can make this ball shoot off and hit a bunch of other balls, and I think that'll be a lot of fun before we end this section. Okay, so how do we do collision detection? Well, how did we do collision detection on walls or the ground or the ceiling? We were able to check, because those were static places, if there was an intersection between the distance of our ball and another ball. So let me go ahead and stop screen sharing for a second here. Turn your guys' attention back to the blackboard. If we have a list of a bunch of other balls, right? We have a ball here, and we have a ball here, and we have a ball here, and maybe we have a ball here. How can we check for their intersection? Well, if we have all of these balls' positions, if we have all of their centers, then for some given ball, maybe this ball in the center here, we can say, all right, how far is my center from this ball's center? I can go ahead and calculate that, and we know how to do that, right? Distance formula, super simple. And we can tell, hey, this distance is way too far. I know the radius of this ball, and I know the radius of this ball, and they certainly can't be touching. And so I don't need to worry about a collision between these two. Let's try this one. This one's also too far. That's no good. This one is way too far. Definitely don't need to worry about that. But this one right here, if I check the distance of these two, that is going to be less than 1 radius, assuming these all have the same radius. That is less than 1 radius apart. And so there is going to be a collision here, right? Because the distance between the centers is less than 1 radius total. And so that's going to be problematic. And so once we've used distance formula to test whether or not two objects have collided, then we can mess with their velocities and have them change velocities as needed. Everybody still cool with this idea? Okay, maybe for somebody that has a little bit more computer science experience, what's the computational complexity of doing this? If I have like n balls, what is the computational complexity of me doing this collision detection? Well, if I need to check for every single ball, if there's a collision, if I have n balls, then in order to check if this ball is colliding with another, I need to check 1, 2, 3, 4, 5 other balls, right? I need to check n minus 1 other balls. Does that make sense? And I need to do that, so I need to do n minus 1 checks for every single ball that I have. So I need to do this n times, which is going to give me something on the order of n squared. And so this collision detection is going to be pretty expensive to do computationally. It'll work for 10 balls or 100 balls. It'll probably even work for 1,000 balls. But anything more than that, and our animation is going to run really, really slow. And so we won't cover it in this class, but I do want to bring up this idea of computational complexity of collision detection in this naive way, because there's an entire world of really, really cool collision detection algorithms that use stuff like spatial hash maps. I wish we had the time to go over it in this class, but we don't. If this is something that interests you, though, this is really, really cool stuff. And you can easily make amazing, like really beautiful, large-scale simulations of like objects that are colliding with one another if you understand how collision detection works at a better, like more granular scale. Okay, for now, this will probably suffice. So let's go ahead and go back to our code and try and code this thing out. Okay, everybody can still see that fine, I assume. Okay, so we've created all of these balls. We need collision detection on them. And so this is getting just a little bit hacky for the sake of time. But what we're going to do is pass all of the positions of the balls to each ball, so that if I'm a ball, I know where every single ball around me is. And that way I can calculate my distance to every single other ball. And so the way that I can do that is maybe just creating an array list of other balls. And maybe I can just go ahead and initialize that here. just saying, hey, this is indeed going to be a list. It doesn't like, balls can't be plural, has to be singular. And maybe we create a very simple function to add a list of balls, like initialize this list. Here we're just saying other balls is a list. We actually need the data of all of the other balls to be passed into other balls. And so we can go ahead and do that by saying set balls. And maybe we pass in an array list of type ball. And we say this dot balls, or this dot other balls equals balls. Okay, this part I'm sure was probably a little confusing if you're a little bit newer to code. All we're doing here is in our main class, we have a list of all of the balls, right? But we need every single individual ball to also have access to that data. And so the way that we are giving it access is by creating a list of other balls that each ball knows, and then saying from this sketch where we have that data, actually, we're passing that into a function that sets all the other balls. Okay, so now that we've done this, every single ball knows the location of every single other ball. And so here, right, in our move function, this checks for boundary collisions. Here we want to check for object/ball collisions. Okay, so how do we want to do this? Well, we want to say for every single other ball, so we'll iterate through our list of other balls. For every single other ball, we want to check the distance between our position and the other ball's position. And so let's get what that other ball's position is. So the other balls is a list. We want to get the ith ball within that list, and we'll do this for every single I. We'll do this for every single ball. We want to get that ball, and then we want to get its position. And we'll call this other position. And now we want to check the distance between our position and their position. And thankfully, I mean, we could write out distance formula. It's super simple. But processing has a distance formula function that calculates it for us. That's going to be called dist. So we can say float distance is equal to the dist, and we just need to pass in the x and y coordinates of our position and the other ball's position. So if you'll recall, that's position.x and position.y for our position, and the other position's x and the other position's y for the other position. And then like we said, if this distance is less than the radius of our ball, then there has been a collision. And so in this case, maybe what we'll just do is invert our velocities for x and y. And this is where we're getting a little bit messy with the physics. Really what you want to be doing is calculating, like, I think it's the arctan between the two balls, and that'll give you the exact angle that they're hitting each other at, because the angle that two balls hit each other at matters for where they go next. We're not going to worry about that for the sake of time, but you are more than welcome to investigate this stuff. It really just is a matter of changing this if statement here. It should be 2 radii. Yes, I think you're right. Yeah, it absolutely should be. Yeah, so somebody pointed out in class that I made a mistake. Let me show you guys where that mistake is. Let me stop sharing here. Okay, yes. What was pointed out was that this value for collision detection should be 2 times the radius instead of just the radius. And of course, that's right, because there is a collision if the distance between the two centers is not just one of these radii, but both of these radii added to one another. So, yeah. guess. Let me go ahead and share my screen again. Okay, so the distance should be 2 times the radius. And I think that should be good. Let's go ahead and run this thing. Okay, our balls are not bouncing off one another. And the reason is because I never actually passed in the data for other balls. Remember, I created the setBalls function, and I never used it. I need to use it over here. So I want to say for every single ball, I need to give it the data about the position of every single other ball. So I want to say balls.getI.setBalls. Okay, that was a lot of repetition in the same line. If that was confusing to anyone, feel free to let me know and we can cover it. Otherwise, hopefully, oh no, this isn't good. Okay, actually, this also makes sense for why this is happening. Does anybody have a guess for why these balls are just like jittering? They're just standing still. Exactly, yeah. So the reason that all of the balls are not moving is because they are actually colliding with themselves all of the time, right? Obviously, their position is overlapping with itself. So how do we fix this? Any ideas? Here's one easy way we can fix it. We give each ball an identification number. We tell each ball what its index is. And we want to say inside of our collision detection, hey, if I am calculating the position with myself, don't calculate it. The other thing that I can do, right, is if a ball has the exact same position as I do, then exclude it entirely. Because if 2 balls are hitting one another, they're certainly going to be hitting each other more than just overlapping exactly. And the positions for like a ball and another ball in the list will only otherwise be the exact same if they are indeed the exact same ball. So let's try that second approach just because it's a little bit faster. Again, we're being a little bit hacky with the way we do things, but maybe we can say if our distance is 0, then we'll just continue. Like we won't get to the rest of this. The other thing that we can do is we can say if our distance is not equal to 0 and the distance is less than 2 times the radius, I think that might work. Yeah, okay, we are bouncing, but maybe that 2 times radius thing wasn't working because as you can see, we're bouncing even when we're not actually hitting all the way, right? Let's see if this gets fixed just by switching it to 1 times the radius. And if it does, maybe we can take a look at why that's the case. So instead of 2 times the radius, we'll just do 1 times the radius. Okay, and yeah, this looks a little bit more promising. Okay, so why might it be 1 times the radius? Because I agree with what you said. It certainly seems like it should be 2 times the radius. Not entirely sure. So probably take a little bit more thought than we have right at the moment. Maybe somebody on Zoom has the answer. Okay, no worries. We'll come back to this. We'll maybe get a discussion about this started in the Slack. Because at first glance, it does seem to me like this should be 2 times the radius if we're calculating distance between the 2 centers. Yeah.
Well, I mean, I guess if they're all the same radius when they hit each other, I mean, that's basically going to be 2 times the radius. I don't know if that's it, but sounds plausible.
Are you saying it should be 2 times the radius?
Well, no, when the balls hit each other, the contact point is going to be in between 2 radii. So maybe that sums to 2. So you just reduce it to 1.
Interesting. Yeah, perhaps. Again, I'm not seeing it super clearly visually, but that's all right. We'll open a discussion about it in the Slack. and really confirm exactly what's happening there. Okay, but this is the general idea. I think we still have the ability to, yep, this ball right here is the one that we can control. So we'll spend 5 more minutes with this. I know we said that we would only spend 5 minutes with it earlier, but we'll only spend, yes. Oh, okay. Yeah, you know what? I might have messed that up. Let's take a look real quick. So in class, what was mentioned was that the parameter that I've been saying is the radius is actually the diameter, which would make a lot more sense. Let's see. Extent is the width and the height by default. That's a really weird way of describing it. But yes, that is indeed the diameter and not the radius. The width of the entire ellipse would be the like diameter. That's how we're thinking about it. Okay, cool. Yeah, okay. This actually does make a lot of sense. Perfect. Open up chat real quick. Did we lose a few of the ball objects somehow? Man, I hope not. That wouldn't be good. We might have. And the reason is because of like improper boundary checks. Really what we should be doing to make this entirely technically accurate is if a ball crosses even a little bit outside of the boundary, we should be resetting its initial position to be inside of the boundary. That's something that I skipped over just because it is a little bit technical, but in some like rare instances that can lead to balls flying out of where we should be. And indeed, actually, if you guys caught that, one did fly out of that end. Okay, so again, maybe something that we can take a look at, or you guys can take a look at for the assignment. Let's see, how are we doing on time? Okay, I think we're okay on time. We'll do one last thing. We'll add a little bit of color, and then we'll call it a day on these bouncing balls. I think this is going to be a lot of fun. We talked about RGB last time. And in the lecture re-recording, we talked about HSB values, but I think the vast majority of people were not here for that re-recording, so we'll cover it real quick again. So when we talk about RGB, we're always talking about our 3 parameters being the amount of red, the amount of green, and the amount of blue, and that makes up a color. Processing has another color mode, which is HSB, and that stands for hue, saturation, and brightness. These are also 3 parameters, also between values 0 and 255. But now instead of controlling the amount of red, green, and blue, it's controlling the amount of hue, saturation, and brightness. And so we'll go ahead and mess with that in order to change the color of each ball. And really what I'm hoping to do is I want the color of each ball to be a function of how many times it has collided with another ball. I think that might be interesting. So the way that we want to do this is I want to keep track of the number of collisions that each ball has had with another ball. I think that should be super simple to do. I can just create a new integer called num collisions, and I can initially set num collisions to be equal to 0. I know every time that I've collided with something because it's right here, and so maybe I can say num collisions plus equals 1. And now when I want to display something, let me go ahead and change my color mode. I haven't changed to HSB, even though I talked about it. HSB, it's super simple. Just got to do that in setup. Now I can set my fill color for my circle to be maybe the hue is what changes with the number of collisions. So maybe we do num collisions. And then we want the saturation maybe to be cranked up to the max, 255, and the brightness to be cranked up to the max, also 255. And let's see what happens here. My guess is that the num collisions, like incrementing it only by 1, might not do much. Yeah, okay, so we're, if you can, I'm not sure if you guys can decipher on the projector, but some of these are a little bit more orange than others, but it's not super duper clear. So in order to just make it a little bit more clear, actually I think it might be a little bit more clear on the projector now, but maybe instead of num collisions plus 1, we just do plus 5 or something simple like that. we should see the effects a lot faster now. Yeah. So you guys can see now our bouncy balls change color based on how many collisions they've had. And of course, we can still move whichever ball, I think it's this one right here, this sort of like lime green turned dark green now, to hit other balls. And so the challenge for you guys is going to be on the assignment to create a pool simulation. You have all of the basics here. You have balls that can collide with one another. You have the ability to move a ball to a specific position. Now the big question is, how can I use this to create a simulation of pool or billiards? And I think that'll be a lot of fun. If you did the pre-lecture videos, there's a really, really awesome video there of billiards being played on like an elliptical surface. I think that's a lot of fun. So if anybody wants to mess with that, that's going to be a little bit more math, but it will be, I think, very, very worthwhile. All right, okay. So we've used about an hour of our time, which means we have about 30 minutes to create one last simulation. I think this one's going to be a lot of fun. This one is one of my favorites for a couple of reasons. One, it's super you totally see it all the time, everywhere. You get a cup of coffee in the morning, you will see it. My friend sent me a picture of his ring that was just sitting on his desk a little while ago, and you can see the exact same pattern inside of the ring. It's a pattern that comes up when light hits the inside of a circle, right? So obviously you would see it inside of a coffee cup, inside of a ring. This is also one of the pre-lecture readings. But if you've seen it before, it is a pattern that looks really, really pretty. It's really, really intricate, and I think it will take us like 10 lines, 15 lines of code to do, which is why it's so much fun. So here's the pattern. This is, I don't know how to clean these properly. Cleaning whiteboards is really easy. Cleaning blackboards is surprisingly hard. But anyway, we have a circle here. Wow, I drew that circle pretty well. We have a circle here, and the way that light hits the inside of a circle is pretty interesting. If you think about the circle as, instead of just being a circle, as a collection of points around a circle. Can everybody on Zoom see that okay? Let me zoom in just a little bit. Okay. So if we think about the circle as a series of points around a circle, then generally the way that light hits the circle is that it starts out coming in from one side, and then it bounces and hits the opposite side in like a pretty interesting way. So if we number our points, okay, I created 13, which is not great, but that's okay. The way that this works is if you have light coming in from a numbered point, the light ray will always go to the point that is numbered 2 times that amount, which is pretty interesting. Again, not great at physics, probably can't explain to you exactly why it works more in depth than this is how the light rays bounce. But we'll be asking ourselves one of those what-if questions that we talked about in lecture 1 with this visualization. So the light ray from 1 will go to 2, the light ray from 2 to go to 4, 3 to 6, 4 to 8, 5 to 10, 6 to 12, 7 to 14, but we don't have a 14. And so the way that this works is it'll actually just modulo, it'll wrap around. And so our 14 will just go to 1. 8 will go to 16. We don't have a 16, but it's the same as 13, 14, 15, 16. 9 will go to 18. 10 will go to 20. 11 to 22, which I think is right here. 12 to 24, which should be right here, right? I think I may have messed this up. But you guys see this general pattern, right? It's a little interesting. We'll do this, we'll replicate this exact same process mathematically using the code, and we'll look at the pattern that comes out. It'll look something like this. It'll look way more intricate and pretty. And the question that I sort of want you to be asking yourself while we create this is, what if the light moved just slightly differently? What type of pattern would that create? Okay, everybody good with this idea? The last thing that I want to talk about is, on the whiteboard at least, or on the blackboard, is how do we actually get these points around a circle? This is just a little bit of, I think, like trig that you have to do. But in general, if you have a circle and you want to get the Cartesian coordinates for the points around the circle, it's just going to be a super simple formula. It's going to be our radius. Let me zoom out just a little bit. There we go. It's going to be our radius. This is the x. So the x coordinate is going to be our radius times the cosine and then the angle. And the y value is going to be r times the sine of the angle. And so in radians, this will just be between 0 and 2 pi, right? And so if we want a bunch of points around a circle, then we just need to interpolate a bunch of values. If we want like n points, then we just need to linearly interpolate n between 0 and 2 pi. And that'll give us the x and y coordinates for every single point around our circle, right? So the way that we'll do this in our code is we will create some number of points, and then we'll draw a line from that point to the point that's indexed at 2 times that point, modulo the total number of points. Does everybody sort of follow that idea? It gets a little bit more complicated when I abstract the like idea out beyond just drawing out the numbers. But yeah, if anybody has any questions, just let me know. It will not affect the pattern that is drawn. The pattern that is drawn will be the same. What it will affect is like how intricately the pattern is drawn. So if you take the same idea and you just do it with like 3 points, that will create a very rudimentary version of this pattern. If you do it with 200, like we're about to, then it'll create a very, very pretty version of this pattern, much more high resolution version. Oh shoot, I've been meaning to try and say the questions before I get them, just for the sake of the recording. So for the sake of the recording, if anybody's listening, the question was, does the number of points affect the pattern? Okay, let's go ahead and share our screen. Let's code this thing out, and then we can call it a day. Awesome. So let's go ahead and create a new processing sketch. Actually, let me save this one so that I can go ahead and upload this to the GitHub later. So let's create a new processing sketch. Again, we'll do our void setup and our void draw. And I think you guys are really, really going to like this one. This one, we're not going to need any objects, right? We're just drawing a couple lines. No need to overcomplicate things. We don't need some sort of object. It doesn't have any like real attributes. We're just doing a little bit of drawing. So let's go ahead and set our canvas size to full screen. We want to keep track of the number of points. So let's say num points is equal to, let's start out with 200. Why not? We'll go big to begin with. And so let's start by just creating the points around the circle. We'll draw the lines after we know that that part is working. We'll also want a radius, right? We want a radius in our equation. So we'll say that our radius r starts out at like 100. So we want to say for every single point in num points, we want to draw out the position of that point along the circle. So we can say for I is equal to 0, I is less than num points, increment I. We can just go ahead and use our formula here. We want to draw a point, and the x coordinate is going to be our radius times our cosine, and then remember it's 0 at the beginning, 2 pi at the end, and somewhere between those two, linearly interpolated in the middle. Any ideas on how we can get what that amount should be? Well, if we know our I value that we're currently at, and we know the total number of points, then we can just create a fraction, I divided by num points, and that fraction will go from 0 to 1, right? Because I goes from 0 to num points. So that all over num points goes from 0 to 1. And if we take that fraction and multiply it by 2 pi, then we should have exactly what we're looking for. We should have our angle. So let's go ahead and try to do that. So we have I divided by our total number of points times, and then in processing, you can just do 2 underscore pi in all caps to represent 2 pi. And that's our x. And then we also want our y, which is the exact same thing, but with sine instead of cosine. Let's go ahead and run this, see if this works. Okay, so we have our circle. We only have a quarter of it, though. Does anybody have an idea of why this might be the case? This is also going to be like a tricky question, especially if you weren't here for the first lecture. Where's our circle being drawn around? Like, what's the center point of our circle? The chord 0, 0, exactly, yeah. And the tricky thing about processing, right, is that 0, 0 is the top left. So if we want the circle to be displayed in the center, we can do a couple of things. We can offset our points, or, and I think this is going to be something that a lot of people use in the future in general, we can translate what our coordinate system looks like. So the translate function allows you to take the coordinate system and say, hey, 0, 0 is in the top left. Let's translate it to a different point. And so if we translate our 0, 0 point to the right by width divided by 2, and down by height divided by 2, our new origin is going to be in the center of the screen. So now we'll draw still about the origin, but the origin will be in the center of the screen. Does that idea make sense? Yeah, so the question is, why is the translate function specific to changing the origin of the circle? It's not. So the processing's coordinate system in general can be manipulated, and oftentimes, especially when we're working in 3 dimensions, we want to manipulate the entire coordinate system. And so there are a couple of different ways to do this. Translate is one of them. You can also do things like rotate or like scale. And so translate is taking the entire coordinate system and then moving it down, and then we're still drawing around the origin. It's just changed. Okay, I don't know how well you guys can see that circle because these points are pretty small. So let me change this to be a circle with, not radius, diameter, 5 maybe. And I'll change my radius for the entire circle to be something like 200, so it'll be a little bit bigger. Okay, so that should be a little bit more apparent. Now on to the fun part. We need to draw lines that go from each point to 2 times that point and then modulo, right? This is actually way easier than you might think. We have an index value for each point, so we can just get 2 times that index value, right? This is, if we consider this index 1, then we know where index 2 is. It's just 2 times the position of index 1 and then plug that into this formula. And so all we want to do is actually go through the process of drawing those lines. And so the way that we'll do this, and please feel free to slow me down if you guys need. I've written this code like a million times because I like it so much. So I might be going a little bit fast. But the idea is, we'll keep this as is. The idea is you want to draw a line from the current point to the next point. So this is the current point, right? And then in order to draw a line to the next point, we just want to take this value and multiply I by 2. Everybody following that idea? And then because this 2 times I might be greater than num points, because remember I goes all the way up to num points. Actually, this should be num points. Because I goes all the way up to num points, 2 times I might be greater than num points. We want to take this entire thing and we want to modulo it. We want to take the remainder of that and num points. And then we want to do the exact same thing for the y. Okay. I'm going to comment that out, and let's see what that creates. There we go. That is the pattern that comes out of this thing that we've drawn up on screen here. Pretty cool, right? If you guys look at the inside of a coffee cup, I absolutely promise you, you will see this exact same pattern. This pattern is a fractal, which is a lot of fun because fractals are what we're going to be talking about next lecture. And here's where we get into the really fun bit. This is the part where we ask, what if? What if light moved slightly differently? If instead of going from 1 to 2, 2 to 4, what if we went 1 to 3, 3 to 6, 6 to 18? What if we multiplied by 3 each time? And the cool thing is, the really fun part is, we can totally do that. And it just involves changing like one number. So we were multiplying by 2 each time. How about instead we multiply by 3 each time? And the cool thing is that this is going to create a completely different looking pattern. If we change this to something like 5, you'll see some semblance of the original pattern, but it'll be a little different. And you know, the cool thing is, these aren't just what-if questions. It turns out, if you have the right lights above you in the right configuration, your coffee cup will actually look like this. Your like ring on your table will actually have this light pattern on the inside. And, sorry, excuse me. You can totally see it, as long as the configuration is just right. So again, my favorite thing about generative art, the scale. So we looked at this for 2, 3. What if we can look at it for every single value? Let's create a super simple animation. This will involve like 2 lines of code, and then we'll call it a day. But I think this animation will be a lot of fun. So right now, we're just putting these in as static values. Instead, let's just call it the mult val for multiplication value. Let's start out by saying this mult val is equal to 2, because that's what we started with. And then we'll take our mult val and we'll just increment it every single draw function. And let me go ahead and increase my radius even more. Ooh, okay, so that filled in black. I don't want that. I'm creating a completely new thing each time. So let me go ahead and change my background to be 255 here. And so I'll be recreating this pattern every single time I run each frame. And that looks pretty cool. It's a little too fast right now, but let's take a gander at slowing it down. Remember, the easy, lazy way that we can do this is just by decreasing the frame rate. Let's maybe have frame rate 2 going. And so you can kind of see, like through this lens, how the pattern forms. It gets all wacky here, and then it gets really, really pretty again. And if you watch this for long enough, you can totally see a couple of patterns that like keep emerging throughout the entire process. And what's really fun is that as we get more and more complicated with this, you're never going to see these in real life, probably. The amount of like lights that you need in order to, have this sort of pattern perfectly set up, just not going to happen. But we were able to simulate it so easily, like basic trig. And I don't know, how many lines of code did we write? Like 10, 15? So this is a short preview of what's to come with these lectures. The idea is going to be set up some sort of cool puzzle like we did here, create a cool visualization, and then implore you guys to change the what-ifs to be as you like. We can totally incorporate lots of cool color with this sort of stuff, make this higher resolution. One of the really cool pieces, I did a little like art gallery with this stuff. Let me go ahead and stop sharing this. I did a cool art gallery with this stuff at the end of my senior year of undergrad, so a couple months ago. And that was a lot of fun because one of the pieces there was a very big blown up version of this pattern, and you could really like get in close and see how intricate it was. But another piece of paper right next to it was just sort of like a story of each of these in order. What happens when the multiplication value is 2, then 3, then 4, then 5, in order, so that you can really just take a step back and see how that pattern changes. So these are ideas for the assignment that will be coming out a little bit later today. This stuff really is fascinating. If you made it through today, like I said, this is probably going to be like about the difficulty level that everything stays at. There might be things that are like marginally harder. Most stuff will be at least a little bit easier, but that doesn't sacrifice how interesting this stuff gets. I think it gets really, really cool. So Friday, chaos and fractals is what we'll be talking about. We'll build off of this idea. And yeah, any questions, comments, concerns about anything? Awesome. In that case, I'm really, really hoping that these lecture videos will be available to you guys as soon as possible. If you have any friends that want to keep coming to lectures, please feel free to invite them. I love seeing more people here in person or on Zoom. Otherwise, that is it. Thank you guys so much for coming.